In this lecture, we're going to talk about how you add forces together, among other things. And this is a methodology that will allow you to add any kind of vector quantity you want together. So this goes for a number of things, force vectors, acceleration vectors, velocity vectors, and even stuff that's a little more confusing. Electric field vectors, magnetic field vectors, etc. And all of these types of vectors, whether they're very, very simple or very abstract, all can get added together using the exact same methods. So there's 3 tiers of methods. Let's start with the simplest. So the first method, which is called the parallelogram method, is the easiest. It's very good for quick results where all you have to do is see what's going on. And what you do is you draw both your force vectors, however they might be. We'll call them force 1 and force 2. And they're both drawn from the same starting point. And then from the end of force 2, you draw force 1. And from the end of force 1, you draw force 2. And if you've done this properly, they should rejoin at the same point. So now you have 2 points, a starting point and an ending point. And you connect them with this vector. And this vector is your new force 1 plus force 2 vector. Now this is great for visualizations, or if you want to double check an answer. You got it and you want to make sure it makes sense. But this isn't particularly mathematically rigorous. It doesn't give you any numbers. So we need a method that gives you numbers. So the second method is great when your vectors are broken up into x, y, and z components. So if we have one vector that's, say, 5 in the x hat direction, and another vector that's 3 in the y hat direction, and 2 in the x hat direction, how do we add those together? Well, we can add like to like, just like with variables or units or anything else. And what we say is 2 plus 5 in the x hat direction plus 3 in the y hat direction gives you 7x hat plus 3y hat. So that's pretty simple. You take your vector, right, whatever your vector may be, you break it down into x, y, even z if you're working in a bunch of dimensions, and then you add together like to like. You add the x to the x, the y to the y, the z to the z. That's pretty simple. But now let's go to the most advanced one. And in this one, we're going to use vectors with magnitudes and angles. So let's take a simple example. The vector has a magnitude of 100 newtons, and it has an angle 30 degrees above the x-axis. It seems like it'd be really impossible to figure out how does this go. How do these numbers break down into an x and a y components? But the truth is we have to fall back on a trick called sines and cosines. And it's likely that you've seen sines and cosines at least a little bit by now. If you haven't, don't fret it. I'll try to go over it very briefly. But it might be worth your time to go out on your own and look up some videos so you can understand this. What a sine and a cosine is a predetermined ratio that you know between the sides of a triangle. And if I give you a right triangle and define an angle, we're going to call this side the hypotenuse, this side the opposite, it's across from the angle, and this side the adjacent. It's adjacent to the angle, it's next to it. And then we're going to define some ratios. So for some angle theta, sine of theta is the ratio of the opposite divided by the hypotenuse. And no matter the size of the triangle, as long as it's a right angle in one corner and the same angle theta in the other, this ratio remains constant. And cosine of theta is adjacent over hypotenuse, and tangent of theta is opposite over adjacent. And all of these values, you can look them up. They're probably in the back of your textbook. They're all in your calculator. They're all available online. So all that remains is seeing how to use them. And the way you use them is you can use them to calculate the opposite or the adjacent. Because in this case, the opposite corresponds to the y hat vector, and the adjacent corresponds to the x hat vector. And it's important to figure out where your angle is to make sure you don't get these backwards. But what we can do is we can say, if sine of theta equals opposite over hypotenuse, then hypotenuse times sine of theta equals the opposite. So if we have a problem where where the magnitude equals 100 newtons and the angle equals 30 degrees above the x-axis. What can we do? Well, let's write it out. We have a triangle. This side is 100 newtons, so that's the magnitude of our hypotenuse. This angle is 30 degrees, and that one's a right angle. So what's this? Well, sine of 30 degrees equals opposite, which is that side, over hypotenuse, which is 100 newtons. Multiplying by 100, we get 100 sine of 30 equals some value x. And then what we say is sine of 30, if you look it up, it's a really well-known value. It's 1/2. So we can say 50 newtons equals x, and we know x is in the x hat direction. Sorry, in the y hat direction. So our y hat vector is 50 newtons in the y hat direction. And we could repeat the same trick to discover the value in the x hat direction. And then once you've broken it down into x hat and y hat, then you can add it together just like we did in the type 2 problem. So you've now seen the three types, which are the parallelogram, where you do a drawing to just get an understanding of what's going on, where you add together vector types, so you have different vectors that you can all add together to get one new vector. And you've seen the third kind, where you use trigonometry to create triangles, break them down into vectors, and then add those vectors together just like we did in type 2. So using these, you can add any kind of vector you want together, and now you're ready to move on to Newton's laws to understand where these forces come from and how they interact.